you can have the questions from your side, please.
Yeah. Yes, sir. First of all, just thank you very much for this going question and answer session. So can you hear me?
Yes,
can you hear me?
Yes, we can hear you.
Is that okay? Yes.
Yes.
Yeah. Okay, thank you. Yes, thank you. My question is belong to this paper negotiate TOI towards a simple, efficient, on-demand reconfiguring data center network. So I think that's an interesting study to get the traffic control in the data center. But I care about something related to this performance under in cache and on-to-on loss in figure 7. I wonder that why does a 5 kilobyte follow makes the minimum go to put because sometimes we get on simulation is the maximum and minimum point is very important to the examine and how to route is the proper scheme. It's that's only. Can you see is figure 7 is a B. You can see is the negotiate TOI parallel network and the negotiate TOI chain clause that has the minimum output. It in as a follow size is the 5 kilobyte. Is our question.
I don't I don't see the order of the negotiator right now. Did he like drop from this meeting? Or
He's here.
oh, he's here.
sorry.
The negotiator Arthur is not here. Should we move to
I thought he
paper
already
first?
here, but somehow maybe there's some communication issues. So maybe can we move to the next question and then we come back to this question later after the order come back? Professor Min, would that be okay?
Yes.
Okay.
That's fine. Yeah,
Okay.
fine. Thank you.
Then we can move to maybe the Philippines part. Do you have any questions for the orders?
Hi, yes, can you hear us?
Yes.
Yes. So I have a question for Rosland for the 5G midband. So I was curious, like when you did the scans, is there an impact on the utilization of the bands? Because it impacts carrier aggregation, right? Like what are the available bands for each area? So does that have an impact on like how many bands are actually available for each country or for each area?
Oh, so can you please clarify one thing for me? What do you mean by the scan?
I mean, like the utilization. So for the midband, right, it's from 1 to 6 gigahertz. It could vary per country. Like, what is the actual assigned bands? Does it actually have an impact on the overall performance? Because like the available bands gives you opportunity where you can do carrier aggregation, right? So maybe if you observe some impact on the available bands for the different countries since they have different bands.
I see. I think that's a very good and interesting question. And it actually related to carrier aggregation, which points to our other paper from the University of Minnesota on carrier aggregation. However, I want to point out that in Europe, what we actually observe, if you read the paper, I think we outlined that in Europe, what we observe is that the operators in each country are assigned or basically the purchase or they acquire wider channel bands. For example, we see that in Spain, Orange uses 90 100, right? And 100 is the maximum mid-band channel as per 3GPP. Now, so because they use this wider channel bandwidth, it's a continuous, it's a contiguous wider channel bandwidth compared to, let's say, in US, right? Because in US, the channel spectrum is very fragmented, correct? Like we see an example with T-Mobile, where T-Mobile uses 20 megahertz and 5 megahertz in FDD mode in band N25, right? And then it uses 40 and 100 in band N41, right? So because of this quote unquote spectrum allocation techniques, right? We have not observed carrier aggregation in Europe yet. Okay, that's when at the time we were doing the measurements, right? However, because of the nature of how fragmented the channel spectrums are in the US, we actually see much more carrier aggregation being deployed, which again, if you refer to our carrier aggregation paper, it actually clearly outlines the different combinations and the impact on throughput. So back to your question now. To answer your question, in our measurement results, because we don't have the presence of carrier aggregation in Europe, it doesn't affect our results. However, in the US, if you look at the throughput that we show, if you notice on, I think, figure 1 of the paper, it actually shows that T-Mobile has 1.3 or 1.2 gigabits per second. And that's due to carrier aggregation. And I think we clearly pointed out that in the paper. I hope that makes sense. And I think that also drove our analysis in terms of like, okay, we want to minimize the impact of carrier aggregation. So we're going to analyze, Spain operators or European operators. And then when it comes to millimeter wave that has been deployed in the US, then we can analyze US carriers. I hope I answered your question.
Okay, thank you.
Yeah, no worries. Thanks for the question.
Okay, thank you very much. Maybe from Thailand side, maybe from Bangkok and Khon Kaen, do you have any questions?
Yes, I do.
Okay, please.
So my question is to Amir from his paper. So since I am the undergraduate student, so I really curious about the where is the edge. Since your result is of the latency is all of roots of ends. So I curious about where is the edge is and what is the spraying and edge directing hops, something about that. So I wonder how it's the results come to the roots of n.
Okay, so I guess first of all, you can hear me, right? Okay, perfect. I guess you're asking, where is this root H coming from, right? So the root H is coming from the fact that so in general, the goal of Shale's schedule was that compared to the existing schedules, which are doing one really big round robin, Shale is doing a bunch of smaller round robins. And those smaller round robins, the way we decided is we first set the H parameter. And what that H parameter says is how many hops are we going to have in the direct path between any two nodes. And so, for example, if you set H to 2, that means you're going to have 2 hops. Now, what we want to do in our case is we want to set, if we have 2 hop paths, we need each node to participate in 2 separate round robins, one of which is going to kind of focus on each of those 2 hops. And we want those 2 round robins to be the same size because we want the sum of their sizes to be as small as possible. And it turns out that the best way to do that is to set them the same size and have them both be the square root of n in the H equals 2 case. And that makes sense. If you imagine putting all of the n nodes in like a grid, and you want to have the length and the width of that grid together be as small as possible, you would want to put them in a square, right? You wouldn't want to put them in like a longer rectangle or anything like that. And then the side length of that square is going to be the square root of the number of nodes. So if we go to a higher number of dimensions, it basically becomes like a higher dimensional version of this. So if we have h equals 3, you can imagine putting all of the nodes in a 3-dimensional grid. And now, you know, the length that you would want for that cube is going to be the cube root of n, and so on. Like basically that's where the h root is coming from. And then what the actual schedule is doing is it's giving you a direct connection to every single other node in the same row and every single other node in the same column. And that's where the 2 different round robins are coming in for h equals 2. It's h equals 3, you have 3 round robins, and so on. Does that make sense?
Yes, it is makes sense. And what it is the spraying? Can you explain more?
Right. So in my talk, I talked about the fact that in the existing systems, we use valiant load balancing. And the reason why is because even if we have a very unbalanced workload, we want to have all of the bandwidth in the system available to us. And this is something we have to do because we've predetermined what the schedule is without knowing the workload. So we want all of the bandwidth in the system available to us no matter what the workload is, even though we can't control the schedule. What we can do is we can make sure to load balance the traffic very, very evenly across the network. So that way we're using all of the bandwidth no matter what our traffic pattern is. And the strategy that we use is called valiant load balancing. And the way this strategy works is you first send from your origin node to a randomly chosen intermediate node in the system. And then from that node, you send to the destination. So what the spraying hops are doing is we randomize each coordinate one by one. And by randomizing each of the h coordinates, that takes us to a random intermediate node. So that's what the spraying hops are doing. They're helping us to load balance evenly across the system. And then we have the h direct hops, which take us from that intermediate node to the destination node.
Okay, thank you.
Okay, thank you very much. Actually, since we are talking about shells, I have a few questions. So you mentioned about the Pareto configuration that you have, right? You have the curve and you have the Pareto.
Oh yeah, that we have a Pareto optimal schedule.
Yeah. Yes. Is that the Pareto optimal schedule like configuration for your schedule, or it is for all possible schedule that you can do in like the flat topologies?
That's a great question. The paper that I will cite here is our 2022 stock paper, where we actually found what Pareto optimal ORNs can do. What we were looking at is, let's say you have total freedom to design whatever ORN schedule you want to design, and then on top of that schedule, you can do whatever routing you want to do. We wanted, based on that, to find the best latency throughput trade-offs you can possibly have. And the way we formulated it is we really wanted to exactly match the throughput bound. So what we said is, let's say you want to design a system that's going to always support a given throughput, no matter what the traffic pattern is. So you want to design an ORN that will always guaranteed support a given throughput for every traffic pattern. Based on that constraint, what is the lowest maximum intrinsic latency you can achieve? That was the question we asked. And we had a lower bound for that, and we also had an upper bound for that. And the way we got that upper bound is we designed 2 families of ORN schedules. In that paper, we designed them from a very theoretical perspective. We weren't considering things like queuing or anything like that. In fact, we actually were using a fractional flow model, which obviously can't deal with queuing. But one of the optimal schedules from that paper is the one that we later used to create Shale. So the schedule that Shale uses is one of those schedules that had an optimal intrinsic latency, like a Pareto optimal intrinsic latency. And actually, because of the H parameter, that H parameter is letting us achieve multiple Pareto optimal points. If you're more curious about it, I would definitely say you should take a look at the stock paper. It is a theory paper. It might be a little bit dense, but we do have a graph of what the Pareto front actually looks like, and it's actually quite interesting.
Okay. And in that paper, the setting of the network, you consider a flat topology, right? You don't consider like maybe 2 like fancy like multi-layer OCS or something like that. Just a flat topology.
We assumed that's what you're gonna have. Like, even if you have a multi-layered OCS topology, it can still simulate what we're expecting from the flat topology, right? All we really need is that you can create the communication between the specific node pairs that are in the schedule. Actually, if we think about this, what would be the best switch topology to implement shale? Actually, making one really big switch might not even be necessary. Really what you need is you need one switch for each of the round robins, because you don't need to connect arbitrary pairs of nodes. So if you were doing a multi-layered OCS topology to implement shale, you might actually be able to simplify that a little bit. You might not have to provide every single node pair to communicate.
Okay. Thank you very much.
But we didn't consider that aspect in our design. It's just something that, you know, happens to fall out.
Okay. Thank you very much. Maybe just maybe short questions about your like a solution for the part collusion and the token mechanisms. In those two mechanisms, you need to like exchange the queue information, right, in order to like pick which node to go. And just curious, like how practical it is.
Okay, so for the spray short one, we actually don't exchange any queue information. We are only using the local queues at the specific node that's deciding where to take the next spraying hop. So basically, as we're sending a cell through the system, when it's taking its spraying hops, every time it arrives at an intermediate node, that node is going to make the decision of which spraying hop to send that cell next. And that node also knows what its local queue lengths are. So what spray short says is, look at your local queue lengths and pick the shortest one. We're not communicating queue lengths from other nodes, and that was actually a very important thing for our design considerations because we really wanted to minimize the amount of information exchanged. Like you said, it's a big concern for implementability if you're exchanging a lot of information. As for hop by hop, we are actually sending the tokens back. Once we send a cell on its next hop, we send back a token. We talk a little bit in the paper about how specifically we do that. The way we do it is we actually allocate a little bit of space in the header of every cell to carry that information across a single hop. You could also think of it as allocating a part of each time slot to carry that token and have it be separate from like the header of a cell. The key thing there is we're only propagating it across one hop. So that makes it really simple to do. It means you also are going to, on average, only generate the tokens at a rate of 1 token per epoch. Because you're only going to receive one cell from every node. So you're only going to generate, on average, 1 token to send to each node in return. There are going to be situations where you generate 2 of them in the same epoch. We allocate space for two tokens in each cell. So that way you shouldn't build up too long of a queue. And we account for all of this in our simulations. We actually simulated all of this, and our implementation is also doing this as well. So we're very confident it's practical.
Okay. Thank you very much. From other pods, do you have questions?
All right, a question for Amir. Could you hear me?
Yes.
All right. So firstly, kudos on the good presentation. I mean,
thank you.
Very easy to understand. Right? We appreciated that, including the animations and stuff. You know, a lot of we could sense that a lot of work got into the presentation. Anyway, a simple question here, partly answered by you just a minute ago. Well, so the paper primarily relied on packet simulations, right? But no simulator is perfect. So what aspect of reality do you think was likely or definitely missed by the simulations?
So we actually did compare between our packet simulator and the hardware simulation of our end host. So in terms of like the accuracy of the packet simulator, in implementing the shale algorithm and the shale congestion control, the shale routing scheme and all that, we're very confident that's doing a good job. If I had to point to one thing, there is kind of an abstraction we're assuming here, which is that you can actually do all of this ORN stuff to begin with. You can actually reconfigure on nanosecond timescales. You can send a message, it will reliably be received, and so on. There's a lot of stuff that by making that abstraction that we're not dealing with. So for example, in a real system, you might have to worry about transceivers kind of like synchronizing with each other and properly sending the data across each individual link. And that's something we don't address in this work. There's things like node failures. We actually do address how you can communicate information about node failures, but the actual mechanics of the failure might be a little bit more messy than just a binary, it works, or it's failed and you know it's failed. And we never simulated the process of a node failing or the process of a link failing. We don't really have anything for intermittent failures either. Now, in our simulator, we did simulate with failed nodes, but we simulated those nodes basically being failed from the beginning of the simulation, just to show what the performance is like once those nodes have failed. In general, I would say the gaps between where our packet simulator is and where the reality is probably the same as the gaps between where our paper is and where reality is. There is a lot of stuff that we viewed as out of scope for this paper, and we didn't address it in the simulator either. We think, you know, we didn't focus so much on the specific like implementation of the optical circuit switching, basically. That is the big gap.
All right, thanks, Daniel.
Someone actually asked a question in the chat. I guess I'll answer that. Congratulating on my paper and seeing I'm expected to graduate this summer. Am I on time for graduating? What's my next goal? Yeah, wait, it was a direct message. Whatever. I'll answer it for everyone. I actually have graduated. I defended right before coming to SIGCOMM, and everyone on my committee signed everything on August 1st, so I am graduated at this point, basically. I will get the degree on August 31st. Next, I'm gonna be on vacation for a few months, and yeah, after that, I'm trying to line up a postdoc right now. It's not lined up quite yet, but that's what I'm aiming to do.
Okay. If there is no questions from others, I have questions for Shooting Lu. I'm not sure whether I correct.
Shooting, yes, yes. Shooting,
Sorry.
yes. No problem.
So I'm just curious. So in your paper, you built a new collective communication library for machine learning, right? And my understanding is that the scope of the library is for one, like let's say one task, right? When you execute the task, you use this library. But in data center, actually there are several tasks that can happen together. I'm just curious how. I know that you for each task you try to optimize it, like the collective communication. But just curious, what would happen if you have several tasks running concurrently, and how the performance degrades?
Yes, that's a great question. So like in our setting, like we were just assuming, because in machine learning training, like usually just get one user to get hold of all the like maybe 32 GPUs. And in that case, you run our scheduler that gives you a schedule. And when you need all gather, it tries to utilize all the bandwidth to help you complete this all gather operation. And in the case like for data center, like there are multiple users, then this user, this schedule that is optimized for a single user might not be good. In that case, you should probably like in our like traffic engineering problem setup, you should put multiple users workload as an input, and the generated schedule will consider all the required workload and give you that schedule. So that is like one thing we mentioned in our future direction, where like our formulation of traffic engineering supports you to add multiple users or workloads, but we haven't done that in current version of our paper.
Oh, okay. Okay. Thank you very much. And I'm just curious about the scalability. I think you mentioned about hundreds of nodes. Just curious, how much can you scale?
Yes. So for current version, we ran simulator for 256 nodes, which is 256 GPUs, and our hardware experiments is on 32 GPUs. 2 nodes of each node have 16 GPUs. Yes. So this current version like just use like the basic version of the traffic engineering formulation. Although the 256 version uses our A-star algorithm, and the 32 version uses our MILP algorithm. So A-star is more scalable than MILP, and we are also like trying to, because there are many traffic engineering solvers or algorithms that can, like from many papers, they all claim they can be bring you many scalability or quality. So we are also experimenting with them.
Okay. Thank you very much. See. I think somehow the author of the negotiator somehow he is not here. So
He's not here, but we can compile the question, and he is happy to answer by the email. So maybe we can do this after the session.
yeah, yes, we can do this for yeah, we can do this offline later. Since
Join the Slack channel. You can do question answering using Slack. SIGCOMM has a Slack channel.
okay, sure,
Yes.
yes.
Okay.
So maybe I have a few questions for Amir about shells. This is like a very general question actually. I'm just curious about like the current state of the OCS, like how like if you look at the negotiator paper, but the author is not here. Actually, they talk about the like arbitrarily reconfiguration, right? But in your paper, you consider the like obvious reconfiguration, like you have a cycle of matching and then just go through it. And
Yeah.
and this and what from my understanding, one of the reason that these two modes are considered is because of the hardware limitation. So I'm just curious about like the future of this limitation. Is it going to like disappear or still be there?
So actually, I will give you a different perspective on this. Both papers actually have a similar insight, which is that when you want to do nanosecond scale circuit switching, you need to know what you're going to switch to in advance. You can't try to switch to something as you're figuring it out. And in our case, the way we deal with that problem in our work is we fix a schedule ahead of time and we never touch that schedule. But what Negotiator does is they have several rounds in a process where they're figuring out what they're going to do a couple of rounds from now. So over the course of a couple of rounds, they figure out what the actual circuits they want to deploy are going to be. And then if you have a large flow you want to send, you have to wait a couple of rounds before you can start sending it at that high rate in order for you to schedule those circuits according to, their algorithm. So both of them are kind of addressing a similar problem where you need to figure out what you're going to do in advance. And that's actually not a technology problem. It's a speed of light problem. It's a physics problem. You can't do better than that. because when you can reconfigure at nanosecond scale, you can actually reconfigure multiple times during a single propagation delay. There's no way you can dynamically figure out what you're going to do during that time period. Like you can't communicate faster than the speed of light. So if you want to take full advantage of your nanosecond scale reconfigurable circuit switches, you gotta figure out what you're going to do in advance, one way or another. And we just took two different approaches to doing that. I think, okay, so in our same session, we did have RotorNet. And RotorNet actually does have a technological limitation where, because they're physically engraving the schedule into like a hard drive, like they're physically like etching a disk with their schedule when they're making their rotor switches. So in those switches, you really cannot change the schedule after. At least if you think about it straightforwardly. Maybe there's other fun things you can do in addition to their switches that would give you that capability, but if you're just looking at the rotor switches, there is a technology limitation that says you have to stick to the schedule. But if you look at Microsoft's Project Sirius, there's no reason why you can't dynamically schedule Project Sirius, and that's why Negotiator was able to do that, because they're thinking about a technology where you can do that. But they still have to figure it out in advance. Does that answer your question?
I see. So
actually, one thing I'll say is, in some of our future work, we're thinking about, what can you do with this pre-scheduled idea if you're able to adapt to the patterns that exist in the network right now? Like, we are also taking into account this, this idea of adapting and figuring out what you're going to do in advance, but in an adaptive way. It's something we're thinking about in our future work as well. But we have a different approach to Negotiator.
Yeah. So it's not the computation of the next schedule is like the one of the problems that like a big problem here, I guess. Right.
The problem of computing a future schedule, I mean, yeah, that's what Negotiator is doing. Their whole paper is all about how they propose to do that. I think they had a really interesting solution. They still do have the problem where it takes time to do that process. Of course, they actually have a way to address this for short flows in their paper. I think it's a very cool idea. I haven't thought about it enough yet. But they do have the fundamental thing where they have to take time to figure out what circuits they're going to do next before they can make those circuits.
Yes. Yeah, I actually like the idea, or like try like put the small flow in the control plane. But that actually the other is not here, because I was going to ask, like, what about if the number of small flow is too high and it reached the capacity of the control plane like channels, then that's going to be a problem for small flows. But it's not here, so
yeah, it's a question I have as well. I not to like kill the paper, but just to see what they're thinking, right?
yeah, not just to kill the paper, just
yeah, no, it's a cool work.
Yeah, I really like that work. Sorry, I asked so much question. Maybe I let others ask questions.
So, if I may, I do have a question for is it real Okubu from University of Illinois at Bernie-Champaign about the backscatter communication? Is he here, or? Okay, I don't think any of the authors are here, so I'll reserve my question for the email that's going to go out. So.
Okay, I think so if there is no further questions, should we conclude this sessions? We try to wrap up this. Professor SIGCOMM.
Okay. Is there any more questions from Philippines or Indonesia? No? Well, thank you so much for of all the authors who take the time to meet with the Southeast Asia SIGCOMM community and reach out to all of us. And this is the second year that we have done this virtual SIGCOMM pods to Southeast Asia, and hopefully we could build SIGCOMM community in Southeast Asia to be stronger and to be have more presence in the community. Thank you everyone.
Yeah, I also like to say thanks to you all for being interested in, you know, our research, right? It goes both ways.
Yeah,
Thank you.
yeah, I agree to that for sure. It's flattering to see people actually being interested in your research, because sometimes it feels like an outline. You know, you work on a problem, you're like, who cares about this? So it's actually good to see that people actually do care.
Yeah, I mean, I think all of us authors think our research is super cool. You know, if it gives you any ideas, please also work on that and, you know, maybe submit to SIGCOMM in the future.
Yeah.
Thank you.
Or reach out to collaborate. We're always
Yeah, that's
welcome
also.
we're always welcome to engage new collaborations and do more cool research. So.
That would be nice. That's a great. Thank you. Well,
Yeah.
perhaps that's wrap up. And thank you for all the parts, and Susha, the coordinator, the moderator of all the questions from every part. I know it's and thank you, Professor Min. Thank you, Made from Manila. Oh, I'm sorry. Yeah, from Indonesia. And thank you, Manila Pots and Konkan and also Bangkok Pots. I know coordinating all these parts from different locations is pretty difficult and with the time zone, but this year we're lucky that the time zone is not much different. So it's much more feasible in conducting this virtual SIGCOMM Q&A session. Again, thank you very much, and hopefully we can continue this activity in the future. Thank you. Bye.
Thank you.
Thank you very much.
Thank you so much. Have a nice day.